All right, welcome back, everyone. Let's get started with lecture 14. First, people who are online, can you hear me? Okay, thank you, Trevor. Okay, let me see. Okay, so topics for today are K-means clustering, self-organizing maps. K-means clustering is not exactly a deep learning machine learning model. It's not a deep learning model, but the fact that these self-organizing maps are based on the idea of clustering, I thought let's dig deeper into K-means clustering, and then based on that, you'll see how self-organizing maps work. So again, we are in the field of unsupervised learning, as we've been doing for the past like 2 lectures. So this is the third one. And again, we don't have label data. And so we are trying to find patterns in the data. And that's what self-organizing maps, or SOMs as they're known as, do. So the basic concept of self-organizing maps is that they do some form of clustering of data, and they work on competitive learning. So there are 2 fundamental ideas on which these self-organizing maps are built. First thing is like clustering the data, and then competitive learning. Now we have like this high dimensional data, and most of the times these self-organizing maps or SOMs, they are used to bring that down into a lower dimensional space. That makes it easier to visualize, easier to analyze, and sometimes we are interested in just like dimensionality reduction maybe, or sometimes we are just interested in compressing the data. So those are some of its important applications. Although now, apart from visualizing, we can also use it for doing some predictions as well. So just by looking at the patterns, we can do predictions, and I have like a small example in which we can demonstrate how to do that. But first, let's like try understanding what clustering exactly is, like what's the mathematical side of clustering. And then because like the idea of self-organizing maps comes from that, so then we'll move on to that. All right. So one of the most popular clustering algorithms, I'm sure you must have used it or maybe heard of it or maybe read about it, is k-means clustering. So what we're doing is we are dividing the data into these groups called clusters. And some of the important applications are like in marketing or customer segmentation. So let me give you an example. So let's say some online platform is trying to do some kind of a promotion, and they want to give out some coupons. Now they don't want to, like, they have some budget constraints, so they don't want to give out those coupons to like every customer, and so they want to do some kind of like targeted marketing, right? And one way of thinking about it is that it's beneficial for the platform to give those coupons to people who are going to spend that in some ways, and they're going to buy something or like use it in some ways, right? And so one way of thinking about it is that how about we do some kind of customer segmentation to figure out if a particular set of customers will buy this or not, or if a particular customer will utilize this coupon or not. And so let me target them. And one way of like thinking about, instead of like going and predicting or doing some kind of because I've never like given out those coupons before. So instead of like going and doing some kind of a prediction using some label data, which obviously I don't have for this problem, I can just do some kind of a grouping or clustering of customers. So for instance, let me just draw this here. Let's say I have some data for customers in which I have like how much like number of hours these people spend on my platform, right? So I can like extract that data. And then the dollar amount maybe they spend on average, right? Spend on average, right? So let's say this is my feature space, just 2 features. So this is my dollar amount, and this is like the number of hours, right? And if I just like go and visualize my customers in this space, right? And let's say I have like this kind of a I don't know, like I just made this up. So most likely I'll be interested in targeting some people like up here because they're spending more time. So most likely they're going to utilize that coupon, and then they have spent like their average spend is more. So then it's more beneficial to go there and pick these customers up, right? So these types of problems where you don't have like a labeled outcome of this particular problem, you would like to like segregate customers into groups of like, okay, this person spends a lot of time, but they're not spending a lot. So maybe they're not like good targets depending on your business application and so on. Like, so you will decide based on like customer segmentation, which group is a better group to target. So in problems like these, when I don't have labeled data, but I have patterns that can give me some good answers to certain questions, I'm going to use clustering. And one way of doing that is k-means clustering. And so that's what we are looking at today. So specifically how this works is that what I'm going to do is I'm going to go into the feature space of my customers, for example, in this problem, right? And then I will randomly choose some points within that entire data set. And so those are known as centroids. Now, once I've selected centroids, my clusters should be such that the distance of each of the points in my feature space is the closest to that centroid. Okay, so this is like a lot of information to process. Let me just like go here and visual. So here you can see that we are able to divide it into 3 clusters, just like my feature space. But the point is, how do we do that, right? So there is a whole process, there is a whole algorithm to get these segmentations or these groups or these clusters. Now, let me just like write this down so that that's clear. Okay, so let's say I have like my data is represented by X. And usually I use some distance measure. So for example, let's say I'm using Euclidean distance, but you can use others as well. And there are variants of k-means clustering where you use different distance measures. So let's assume we are using Euclidean distance D, and that D is used to calculate the distance of a point X from its centroid. So for like generally speaking, I'm able to like this D is a distance between 2 points, any 2 points. But now I'm interested in calculating the distance of a given point X with its centroid C. So basically, I'm going to compute the Euclidean distance between the centroid and every data point, right? So that's the fundamental idea. And my output is going to be the set C that partitions like my data in C1, C2, and so on, sorry, C sub K sets, right? So my goal here to calculate this distance and cluster together these data points to any one of the centroids in these like K different centroids is that I should be able to partition my data into K different partitions or K different clusters, right? So that's why that's what this signifies. So what exactly am I trying to do when I'm trying to create these clusters or these like different groups as such? So thinking about that, like the overall idea here is that I'm doing 2 different things. The first thing is that I'm computing like some function phi sub c, and let me just like say that this is for any point X in my data, is that I'm trying to minimize within a cluster. So for example, C belongs to like this big C, any of these C's, Ci or Cj, this distance. So that's the first thing I'm trying to do. Basically, if I have a centroid somewhere here or a centroid somewhere here, I'm computing the distance of each of these points. And the sum of those distances should be like the minimum possible, right? That's the first thing, but I'm not done here because I have a larger problem. Then this should apply to like all the clusters that I create, right? So whatever, like if my point belongs to this cluster, then in some ways I have to make sure that this is like the nearest centroid for this particular point and not this one, right? Similarly, if this point belongs to this cluster, then I have to make sure that this is like nearest to this centroid and not like this one here. And so based on this, like I'm assigning my data points to different clusters or different partitions, right? So my overall problem is to just minimize for like my entire data set, right? This distance X, and usually it's distance squared, but again, as I said, it could be like squared, like it could be Euclidean, it could be Manhattan. It depends like on what problem we are solving. So that's a high level idea that like I want every point in my data set to be assigned to its nearest centroid. Of course, the question remains, how did we come up with the centroid, first of all, right? And like, what are these centroids? And we'll answer that. But this is the problem that I'm trying to solve, that I'm trying to minimize the sum of squares, distances from like for every point within that cluster. That's my fundamental goal. And so that's how these clusters get formed. All right, so coming back to like, what are these centroids and how do we get like these centroids? So there is this algorithm known as Lloyd's algorithm that is used to like get this. And there are other algorithms as well, but this is the most popular one. And so what happens is that I'll randomly select some points that are centroids, right? So I'll just, let's say I selected like this as, so let's say I like randomly selected some point here as C1, and this was like C2, and this here was C3, right? And then what I do is that I compute the distance to each of these centroids with like the rest of the points. And then obviously, for example, like the distance of this point will be computed with this, and with this. So the minimum one is this one. So it is allocated to this one and so on, right? And so obviously when you have like the first iteration done, that means you have allocated each of the points to each of the centroids. Then you recompute the average distances within a cluster, right? Because you will, like, depending on the allocation, you might have an updated centroid or an updated average. So that might be a point in your cluster, or it might not be a point. It might be an imaginary value, but that's fine. It can still be a centroid. And then you keep repeating that process until the centroids stop moving. Because like initially what will happen is that this was a randomly assigned point. And let's say I created some cluster that had like this value, right? And then I created the actual averages here. And then maybe I came up with a centroid here, and then I reassigned all the points. And then maybe my cluster came up to be something else, and so on. So this like keeps itself like updating until you see that the C1 is no more like significantly moving, or the C2 is not significantly moving, or my C3 is not significantly moving. So that means I have assigned every point to the nearest possible centroid. Of course, like there are downsides to this algorithm, but the fundamental idea here is that I'm trying to minimize the distances of like every point within the cluster. So I'm like trying to minimize the average distances within the cluster. And that sometimes is known as, what is that? Within cluster sum squares distance, or sometimes also termed as inertia. Right, so in some ways, I'm trying to minimize this value, this inertia, so that like I have the best possible clusters there. Right? Now, another question that could be of like our interest is how many clusters, because I just said that I begin with like 3 centroids, and then I allocated points to those 3 centroids, right? But I could have started with like 4 centroids here in this data set, or I could have started with 10 centroids here in this data set. And then according to that, I will get like different clusters, right? So what is like this value of K? Because I just said this is like K means clustering. So I have like these K different clusters, but how do I decide K? So there are many ways of doing that. 2 of the more popular ones, like the first one is elbow method. I'm sure you must have come across this if you ever saw K means clustering. So what happens is like I compute this like within cluster sum of squares for like for all the points for every cluster, and then I sum them up, because remember I'm trying to minimize that, right? That was my objective function. So if I try to plot that here, right? If I try to plot it with like the value of K, which is like 1, 2, 3, and so on, and this, let's say, is like my objective, right? So usually what happens is that, let's say I have just K equals 1, right? Which means everything is within that one cluster. So this like within, that is not minimized. My objective function is not minimized. So most likely I'll have like a higher value. But then as I start like increasing the value of K, this begins to come down. So which is good for us. And so we can just like keep increasing these K values. And eventually what happens is that you get this elbow kind of a curve. And this actually tells us that somewhere here should be your like best K, because if you look at it, like the information gain that you're like the information gain meaning like the within cluster sum of squares is definitely going down, but not as much as you would like, because there is that side that you're putting in a lot of effort to just like get this much gain. So that means like whenever that elbow or that curve comes like into picture, then you can just like stop at that K value. And then obviously it depends on your data and the problem that you're trying to solve. So this is one way. This is the elbow method. The second one is the Silhouette method, and I think it's a nice Wikipedia article that talks about it. I don't remember if I have the link here. Okay, so in this one, we are not just focusing on within cluster sum of squares, but we are also interested in between cluster sum of squares. Meaning, if we just like go back here to our lecture notes, now notice that like, let's say there is this point X somewhere here, right? And I'm trying to find the best distance of this point with like one of the centroids. And that should be the minimum one. That's why I assigned this point to this like red cluster, right? But then I'm also interested in that point being as much away from the other clusters as possible. So there are two metrics in this case, and this like Silhouette method, that you're not just interested in like how close your point, your X, is from the center or from your centroid, but how far away is that point from the other clusters, from the other points. And so you include both of them, and then you come up with a coefficient known as like the Silhouette value or Silhouette coefficient. And this is like the formula for that. And obviously you don't have to memorize this, but think of this as like a flipped version of like the elbow method that we saw. So if we just go and like average this value, let me just give you a high level idea of how this works. So we want the maximum of this, because like this actually signifies how much like away this point is from other clusters and how close is it from the centroid, from its own centroid. So it like encompasses both of them. So in some ways, if I have like something like this, a graph like this, and this is like K values, like 1, 2, 3, and so on, you will like most likely get a curve like this, like an inverted curve. And you want this value to be like as high as possible. So it's just like the inverted of the elbow thing, right? And so this, most likely in this case, this is the maximum that I can achieve. And so this is going to be my K value, which is 2. So this is another way of figuring out that for my data, this is the best K possible, right? So two methods. The most popular one is, of course, the elbow method. And this is the other one. This is the, this method actually encompasses two things. That's all you have to remember. All right. So that was K-means clustering. Let me go back to the lecture notes and see if I... All right, so here is the algorithm step by step that we just talked about. So choose the number of clusters K. So you begin with some like random value K, right? And then you just select random points from the data as centroids. And then you assign points based on their like distances. Mostly it's Euclidean distance. It could be something else. And then you compute the centroids of these new clusters. They could be a point in the data set, or they could be like some value, which is not even a point in your data set, but then it is a centroid still. And then you just keep repeating these steps. And there are certain stopping criteria for this. As I said, the centroids of newly formed clusters, if they do not change, then you stop, right? Or if you don't see a lot of reallocation of points, then you stop. Or if you have a predefined maximum number of iterations and those are reached, because you know that in this problem, there won't be much value added to my clusters. If I just run it for, let's say, 100 iterations or 50 iterations, you just stop. So those are three ways in which you can like run this algorithm. All right, so that was the first part of today's lecture. That's one of the important building blocks of self-organizing maps, that this distance measure is important. And another thing, like if you think about this K-means clustering, what we are trying to look at within my data is similarity between points. And that's the fundamental idea behind SOMs or self-organizing maps, that I'm trying to look at similarity between data points, and I'm trying to come up with some values that actually represent the data, and they are very similar to the data. Okay, so that's something that we're doing in k-means clustering. We are trying to look at similarity, and then we're trying to group together data points based on similarity, right? Okay, so that's that. Let me see if there are any questions so far before we move on. All right, so that's pretty straightforward. So I assume that's okay. Next, okay. So as I said initially that we have two concepts that are important for self-organizing maps. The first one is clustering of data, which we just saw. The second one is competitive learning. Now, competitive learning is a different type of learning paradigm. We did see some of that in the GANs network that we talked about, in the sense that there were two networks that were kind of competing with one another, and they have like different goals. So that's similar to what competitive learning, but not quite. Because what happens, like until now, we've seen feed-forward neural networks and other variants of neural networks, and we've been updating weights to correct some error, right? So that's what we've been doing, like take the loss, go and update the weights based on the loss, and then keep iterating until you see that you've like reached a particular, like minimize the loss, right? But in competitive learning, we are not trying to do that. In competitive learning, you will have neurons, which will have some activation. And I would say the definition of activation is a bit different, in the sense that you're trying to get one or two activations based on how close they are to the input. And also, like, you also rank in some ways these different activations and get the winner. And the winner is the one that gets updated, and not like everything like in a feed-forward neural network or any other neural network you've seen. We train the network using backpropagation, and we update like almost everything, almost every neuron. So in competitive learning, that's not the case. We are not going to update everything. We are just going to update some selected neurons. And the update is going to happen based on how close those neurons are in some ways to your input. And that's the idea. Now, there are different competitive strategies, right? So some of the strategies, they include only one is the winner. Some of the strategies include that a group of neurons can be winners. And some of them include the strategy that one is the winner and the neurons around that winner are also in some ways winners. They're close to that winner. And so they should also be updated. It's that kind of an idea. So if we look at like a very clean competitive type of a model, that's known as the winner take all strategy. So then only the winning neuron should be updated and the remaining neurons should remain unchanged. That's the idea of like competitive learning. And there are many variants of competitive learning. One of them we'll see when we discuss the self-organizing maps. And as I said, within self-organizing maps as well, you'll see a lot of different variants of competitive learning. Okay, so here is like, these are the steps that are usually applied in competitive learning. Let me just like quickly give you a high level overview. Okay, so the activation here is the difference between your input and your weights. It's not weights multiplied by your inputs. It's slightly different. And this could be like Euclidean distance, this could be Manhattan distance, depending on like whatever our distance measure is. So let's say like for some pth neuron, right? And some x, this either this or the square of this, depending on like whatever we are using as a measure. This is my activation in these models. And the activation is computed for every neuron. And depending on like the problem that we are interested in, most likely we are interested in having like looking at the neuron that has the highest activation, and that is my winner, right? So that's the first step. And then the second is the update rule or the update step. And the way this update step is applied is like very similar to what we've seen before. Some learning parameter, which is going to be my input parameter, and then x minus this weight. So just think about it. Here in my update step, I don't have like any derivative or any activation involved. Rather, it's just a difference between my input and my weights. That's important because here, if you think about it, I'm just looking at some distance measure in competitive learning. So I just like figure out, okay, this input is this much away from my weights. And so let me not update it. And this neuron is pretty close to my input. And so let me update it. So that's what happens. And the one that has like this highest value of this activation wins, and that value is updated. Okay, so that's that. That's what competitive learning is all about. And now what we're going to do is we are going to combine my competitive learning paradigm and the clustering paradigm. And then I'm going to create a new model that's known as these self-organizing maps, right? Or sometimes also known as Cohen maps after the inventor. So let's look at them. Okay, here's a small section on vector quantization that I just added because it's a very well-known application of competitive learning, but I think I already talked about what this is. In addition to this term, you can also add a sensitivity term, which could be an input parameter, and you can control it, meaning how much sensitive a particular neuron should be to a particular input, right? Sometimes this is subtracted, sometimes it is added, depends on the problem. So this is like a small note I just wanted to add. If you come across vector quantization, you just know that that's like an application of competitive learning. Okay, so that was the background on this self-organizing maps. Let's actually look at what these self-organizing maps are and what information do they carry. And I have a nice like example here. So first actually try to understand this example and then we'll see how these are built. Okay. So I got this, I think from this source, if I'm right. Okay, not this one. This is, I think, yeah, here. You can also check this link where I have this in the lecture notes. This picture source link is the one that leads to this one, and this data has the world poverty map, and this self-organizing map that I'm going to show you has been created using like a lot of attributes of each country. Not just that we know that this is the poverty index, but there are other things like the happiness index, the average age, and the average income. All those features have been taken together to create this map, right? So if you just like directly look at this map, like this is what a self-organizing map or a SOM looks like, right? And it doesn't really tell you a lot except that you see these country codes here, right? That's what you're seeing. Like it doesn't give you any information. But if you look at this map in conjunction with this input data, so they had like some kind of color coded representation of each of these countries, right? And what they did is like this was based on like directly taking the features and computing some index and then getting this color coded map. But the self-organizing map did not know that. It just took the features and then it just segregated, or if you think about it, created some kind of clusters of different countries. And the thing is that these like the color code actually puts countries that are very similar to one another in terms of their features, like the happiness index, the average income, the average age, all together. So that's how this was created. So as you can see, like many of the countries that are very similar in a lot of like their indices or their values in the features, they were grouped together versus the ones that were like very different from these ones were grouped together here. And many of the countries that are similar to one another are grouped here, up here, right? So what this is showing is that I have a lot of input features, but based on those input features, I have extracted all that information and I've brought that down into a two-dimensional representation of that. That's the first thing that I see here, right? Of course, like I can utilize this into forming these different clusters and then doing some kind of targeted like application on these countries, right, on this data. But the first thing that I see here is that this data had a lot of features, and I'm able to bring that down into a two-dimensional representation of those features, right? So let's try to understand how these are created and what exactly goes into like each of these. And by the way, if you're looking at this like hexagonal structure, that's nothing great. I provided a link on how to create those maps. So if you just like go to, I think this one, article, this tells you how to create the hexagonal heat maps. But the important thing is that we have to understand how to get that structure there, right? So this is just like in addition to what we'll see today. And this is what they're doing. What we'll see today is this lattice structure or this like these rectangles. But here this article talks about how you can create those hexagons from those rectangles. So I'm going to focus on the rectangles. Okay, so that's a small addition, but just don't worry about it. If you don't get the hexagonal structure, that's fine. It's just like a way of representing this, right? But we need to understand how do we get the clustering together, right? That's our goal here. So let's actually begin. Now, this is nothing but like a neural network. So the way we create this, why am I getting this Google Scholar thing up here? For some reason, this is like really annoying. Okay, it won't go. Just leave it. Yeah, I don't know why this is showing up for some reason. If I use a PowerPoint, then people who are online, most of them, they don't see that. Okay, so think of, okay, this Google Scholar for some reason is stuck with us. So let's say we have like these three inputs, like x1, x2, x3, and these are my features. These are my different features. And let's say you have like these set of neurons, and I'm having like 9 set of neurons. Or think of this as a hidden layer. But these are not like different layers. This is like a 2-dimensional layer. So basically, these are some neurons that I'm just like visualizing like this, right? And so what's happening is that this is a fully connected network. That means it's connected to all of the nodes, right? And so similarly, this one is connected to all of these, and so on. So this one is connected to all of these, and like. So if you think about this structure, this like 2-dimensional structure, this is my output self-organizing map, right? So it's a 2-dimensional output. This is also known as like a neuron's lattice, and that's the spelling. Now, and that's the output that I get once I take all that input and then compute some values. But obviously, we have to see what values do we compute. Now, if you think about this structure here, I can just flip things over and like, let's say this is again my x1, x2, x3, right? And instead of like visualizing these neurons in a 2-dimensional kind of an output, I can just like put all of these nine of them together. And this is very similar to what we have seen before, right? So all of them like fully connected. It is the same thing that's happening, except that the way we are visualizing this or the way like we are representing this is like a 2-dimensional structure. So basically like every input is connected to like all of these. And this, instead of like going to a higher dimensional space, like it's losing some dimensions because I'm trying to visualize it in a 2-dimensional space. So I'm going to show you like what these, like obviously these have weights, right? And how these weights help us get this kind of a structure. How do they help us? Because this actually looks like any feed forward network, right? But there is a catch to it. That means like these neurons, they don't have our non-linear activation function anymore, but rather these neurons are points in space. These are like data points in my feature space. Okay, how to understand that? Let's focus on any one of this. Okay, so this annoying Google Scholar won't leave us, but let's, okay, I thought this time we'll get rid of it. Okay, there are 2 of them now. Anyways, let's focus on just this one thing. So I have x1, x2, x3, right? And 1 neuron. So this is like, let's say neuron number 1, and obviously we'll have 9 of them, right? And just consider like this one. Now, I talked about weights, right? And when I talked about competitive learning, I said I'm trying to find the difference between the weights and my input. So what exactly is that? Well, let's consider that I have like this weight from the first input to the first neuron, and then the second input to the first neuron, and then the third to the first neuron, right? Yeah, Mason. But I think then that'll take a lot of time. I'll try that. Yeah, I agree. Okay, so I'm like focusing on this one input, right? And what really happens is that I don't sum these up, or I like for now, and I don't like provide any activation on these. Rather, this node 1 can be thought of as a point which has like these dimensions, this W11, W21, W31. So for example, when I have like the second node here, right, it will also have like W12, right, W22, W23, and so on. So like each of these nodes is a point in my input space with like these dimensions. Sorry? Yeah, you're right. The third node to the second one. Yeah, that's right. And so on. So I'll have like the ninth node and I'll have like these values for each of the nodes. So now this is different from what we did when we were talking about like other neural networks. Now these weights are like, consider them like the character, it is a characteristic of my node. It's not an output of my node. It's in some ways defining the presence of my node in my input space. So what exactly, so like just imagine this as some kind of an imaginary point in my input space because it has these values, right? Because like what is my input space? This is my input space, right? And I'm trying to somehow, so like obviously we initialize these weights with any values and then we update them based on the update rule that we talked about. But let's say I have just initialized them with some initial values, right? So I have like 3 of these for node 1. I have 3 of these for node 2. So these nodes are in some ways there in my input space. They have some representation in my input space. They are imaginary, they're not real points, but they are so like, is everybody getting this idea of what I'm saying, trying to say, right? So basically this node is like a representation of these points. It's not like the same thing as it used to be in my neural network. That's the point. Of course, we use the same terminology here, but it's like very different in like self-organizing maps. So how does this like help us? How does this help us? Well, it helps us because remember in competitive learning, you are interested in clustering and you're interested in calculating the distance of these nodes from your input data, right? So how am I going to do that? Let's consider node number 1, right? So what I'm going to do is I'm going to compute the distance of this node 1 with my input, right? Because I can do that because it's just like representing a point. So in some ways, I can write like node 1 equals, let's say I'm considering Euclidean distance. Of course, we have to be consistent. So let's say I'm considering this is the formula for my node 1. So xi minus wi1 squared, right? And then I compute that value and I get some like 1.2. I just made that up, right? And then I compute the value for node 2, right? And then I get some like 0.9 and so on, right? So maybe for node 3, I got 0.3. And I compute that for all the 9 values. But now remember in competitive learning, okay, this is, in competitive learning, I said that there is this like winner strategy, like either one could be the winner or like more could be winners. Let's say that we have like one winner, and that one winner is going to be the node that is nearest to my input. Because what exactly am I like computing here? I'm computing the distance of my node from X, from my input X, right? And just like consider this as one row from my input. Sometimes what people do is that they take like 3 to 4 rows and then compute that, average those. That's also a possibility. But like for a very simple idea, just consider there is like one row, one input row, and like these 3 values. So I can do that, right? I can compute this distance for every node. And then select the node that has the minimum distance, which in our case is node 3, because this is the node that's nearest to my data, right? Based on like my Euclidean, my idea of Euclidean distance, this is closest to my input, and this is what I want. All right. So how does this work? Well, I found node 3 as the nearest point to my input. So this is known as my best matching unit, BMU. So you'll come across that term a lot. So once you found your BMU or best matching unit, you make your weights or like these weights for node number 3. Those 3 weights will be updated only. Only the winner is updated. The rest of the weights stay the same. Those weights are updated. If you think about it, like what's really happening here is that only the point that's nearest to this input is updated in such a way that it comes even closer to my input because I'm updating it. It was already close and then I'm updating it as well. And I'm keeping the rest of them away. So in some ways I'm pulling it. Yes, go ahead, Steve. Yes, exactly. So you can imagine that these nodes are like your initial centroids, and then you are updating them based on the distance, just like we did in like k-means. So that's the idea, yeah. And always think of these nodes as like some form of representation of data in the feature space and not as the nodes what we had in like our neural networks. They are different, right? But somehow, I don't know why, but maybe because the roots are in neural networks, that they use the same terminology, but it is sometimes like misleading. All right. So going back to this is the core of your algorithm. That's like mostly you're done once you've like found your best matching unit. For some reason, I just keep forgetting the B. And then like what you do is you update for that best matching unit. And then comes the second row, right? You will have the second row. And maybe there you'll find another best matching unit. But then what you're trying to do is that's another new point. And you're trying to find a centroid for that new point. And so it could be the same best matching unit or it could be a different one. But then you're going to update based on that best matching unit. And then eventually you're going to pull that point closer to your centroid and so on, right? So let me just like quickly show you what actually happens, what goes on in this. If I'm able to draw this. Okay, so let's say you had like these, this is how they are like represented. Let's say I had like this kind of a structure for my lattice. And this is my first like BMU, so I'm calling it 1, right? The second time this was my BMU, so I'm calling it 2, right? The third time this was my BMU, and so on. You can get different best matching units for different inputs because obviously you are trying to match the best possible node to the nearest input. And then in this algorithm, what they do is they don't just update these weights. Of course, as I said, like in a pure competitive learning type of an environment, you should be updating only these neurons. But they've added like another complexity to it that they update like a radius of points, some R radius. I'm going to talk about it. So like the points that are near with this point will be pulled closer together. And the update is such that this point, the actual BMU will be updated the most. And the ones that are nearer will be updated less. And then like as we move further away, will be updated less. So that they form some kind of like a relationship with one another, but not quite, because it depends like what happens in the next iteration. Maybe this point will move away and so on, right? So that's how we get the final, this color-coded kind of structure, this kind of a clustering kind of structure that this goes on. So there are a few things about self-organizing maps, and I would like to summarize them. And one of them is this like radius thing, if I remember correctly. So what, like the original paper, the one that introduced these self-organizing maps talks about this radius. They recommend that this radius should be decreasing with every iteration. They should keep decreasing it until it like shrinks to the minimum possible, so that like you have like really good clusters, right? So one way of doing that is that you can have some kind of an exponential decay, and the paper actually talks about it in detail. But then you can set up some parameters that have like this radius value as exponentially decaying with every iteration. And that takes care of the fact that you have like smaller radiuses. And like also it makes like intuitively it makes sense, because initially if I had like larger radiuses, you'll have a lot of overlaps. So the same point is belonging to many of those. But eventually when you have like run your algorithm for a lot of data points, those data points start to get segregated from one another because you're computing the distances and like pulling that away from one another. Right, so that's what the paper talks about. And another important thing that the paper talks about is this like weight update. Let me write it down. So slightly different from the equation that I wrote earlier. So I will just write it here. So any t plus 1 iteration is going to be my weight at the tth iteration plus some omega of t. I'll talk about what this is. And then the alpha, this we talked about already. So input minus your weight. Okay, so what is this? This is like my learning rate, similar to what we had in our neural networks, like the gradient descent update. But sometimes this is also like exponentially decaying, depending on if like how fast we want to shrink and like what we want to update. So obviously it depends, but this is like the learning rate. And it's a hyperparameter, so okay, what is this like omega t? So this omega t has a value that the paper talks about, but I'll give you a high level idea of what this is calculating. So this is the distance of like BMU over some constant. I'm not going into that. So what we are trying to do is like here, this omega is like again an exponential function, right? And it's a function of this distance of like every point with the best matching unit. So in some ways, like the update happens based on like how close a point is to your best matching unit, right? So the weight update actually takes that into account. But in most like recent BMUs, they have like redefined this and there are like different ways of capturing this. But yeah, that's what the paper tells us, that if a neuron is closer to a BMU, distance is smaller. And so this tends to like 1, right? So those are small like details that I didn't add earlier. Okay, so that's what a self-organizing map or SOM is. Here I have like summarized the steps. So you will initialize the weights. Weights are like nothing but these nodes that are points in your feature space. And then the input vector is selected from the data set used as the input, like the first row, remember? And then your BMU is calculated. The best matching unit is calculated. Radius of neighbors is updated, first calculated and then updated. Next time, as I said, it should be exponentially decaying, right? And then each weight of the neuron within the radius are adjusted to make them more like the input vector. What does that mean actually? If we go back to that Wikipedia article, that actually shows us a very nice visualization of what goes on. So if you look at this picture here, this is a nice illustration of what's happening. So let's say this was my map. This is like the space where my neurons are, this one here. And this is a space where my training data is, right? And in some ways with the weight update, I'm trying to pull this map because I'm updating the neurons and not the data, right? So the data stays where it is. This map is pulled closer, like point by point towards this until it actually fits in some ways or like really overlaps or takes the shape of that training data. This is a good visualization showing us like what exactly is happening when we are doing those updates. And we are doing the weight updates specifically. Okay, and here is the weight update in the paper. As I said, this is the omega and this is the alpha, and here is the distance measure. Right, so this is the exact weight update that happens. Another quick look at this one here. This is a very nice illustration of like one of the application of US Congress voting patterns. And what they're trying to do here is, let's see, how do you make it? Yeah. So as far as I remember, I looked at it some time ago. So here are like the initial clusters of like 2 different parties, obviously. So that's the first one, right? The input, this is the input table. And the input table has like a row for each member of the Congress and like what their voting like result was for a particular issue. That's the input data, right? So that's, I think they talk about it here. Yeah, the input data was a table with a row for each member of Congress and columns for certain votes containing each member's yes or no, right? And then like some people did not vote. And then the SOM algorithm arranged these members in a two-dimensional grid, placing similar members closer together, but on different features, right? So first of all, like here, this is like a party-wise difference. And this, I think this one is telling us the dark ones are like the points that are really away from their neighbors. And the white ones are they are very close to the neighbors. So like that's why they have like the borders are white and then this is like black, right? And more interestingly, if we look at any of the issues, for example, if we look here, like border protection, anti-terrorism, something, that's what this is saying. This here has clustered together based on their like voting outcomes, like yes or no. So I think the red ones are the yes and the blue ones are the no's. Let me quickly check that. I think they had it here, right? The input. Yeah, so blue means a no and red means a yes, right? So this is like one nice application of how like we can use them. So this is more from the perspective of data visualization, but this is not all. Like you can actually use it for like predicting things. For example, I have a small example here, and then we'll jump into this. So one small example is like fraud detection type applications. Of course, like sometimes you have labeled data for fraud detection. If you have like labeled banking data, that's good. But if not, one other way of doing that is that you can create clusters of customers. And if you think about it, like all the features and the data set I'm using is, by the way, this one. Okay, why is it? Uh, Okay, I think I'll have to update that link. I know that there is a credit fraud detection. Maybe we'll have to Google that. Australian credit approval. Okay, regardless, the data set had some features for customers and like they have values for different features, and then utilizing that, can we predict that a person like would default or not? And like self-organizing map can be a good fit here in the problem like this, because maybe we don't have like the label data that this person defaulted or not, right? Because you know that kind of data is like pretty imbalanced. And so that's why in applications like these, we can check for outliers. So if you're looking for outliers in your data set, this could be a good exercise. And here, this is like something that you must have seen. One thing that I would like to point out is that this is the library that I'm using, Minisom, but you can use other, there are other libraries, especially with TensorFlow, there is another library that you can use to create these self-organizing maps. But regardless, when we visualize the results, this is what it shows, right? And this is a self-organizing map. And if you look at this value here, the value that I'm computing here is that this is the mean distance of neurons from like each other. So if they are like really clustered together, they are very close to one another, that means the chances are that they most likely won't default, right? So the outliers are the ones that are very like are far away from other neurons. So that's the basis for this. Like as I said, that distance could be anything. You decide what that distance is. So like I decided that distance is like the mean distance between different neurons, right? So these white ones are actually the outliers in this case. So again, like this is a very simple application of like using these self-organizing maps, and they're not just for visualization, but you can also predict things using them. So that's that. And then there is another paper, if I remember correctly. Yeah, this one that talks about the usage of self-organizing maps. So what they're doing is they're using a denoising autoencoder that we looked at earlier. And then the output of that is utilized to visualize the outcome for a certain problem. Okay, not this one. I'll just quickly show you what it is doing here. So this is a simple encoder-decoder type structure, and then that output is taken to just project it in a two-dimensional space. and visualize the outcome. So sometimes like you can use this like self-organizing map in conjunction with other models, on top of other models, and not just for dimensionality reduction and not just for data visualization. So this is one very good example. It's like one of the recent papers that you can check out. But yeah, this is another important application. Let me quickly check if there is anything that's left. This one, I think, talks about Python implementation. Yeah, this one, I think, talks about, I think this talks about, yeah, how to implement it in TensorFlow. So that's, yeah, this one here. So I haven't used TensorFlow, but here they're showing how you can like write a class for that and then implement that in TensorFlow. So yeah, that's another good resource. So these are some of the readings that I would like recommend everybody to go over at least once. And you might want to utilize that in whatever project you're like working on. You might want to utilize self-organizing maps to just like maybe visualize your data, right? That could be a useful tool. So that's something that you can have like in addition to what you're doing already on your projects. All right, so I think that's all I have for today's lecture. And let me quickly see if I missed anything. Talk about this. Right, any questions before we end today's lecture? And yeah, generally speaking, I'm trying to keep the lectures shorter so that you can utilize this time to work on your projects, because we don't have like extra lab hours or anything. So that's why I don't want to like dump too much information on you all. So yeah, that's all I have for today. If you don't have questions, so that's it. Thank you. Yeah, that's a good question. So yeah, in fact, that was in my announcements, but I forgot to talk about it. So there is a rubric that I'm going to post on the discussion forum either today or tomorrow morning, because that will actually give you a better idea of what exactly I'm looking for and what is the breakup of points. So that I'm going to post either tonight or tomorrow morning. Okay, let me see. Oh, I'm sorry, I didn't check your question, Sean. Would nodes? Yeah, I think that was answered. Yes, nodes are like centroids.